Our universe holds a secret far stranger than any science fiction. You are about to explore 30 theories that suggest everything you see is just a fraction of reality. By the end, you will have a new framework for understanding existence itself, from the tiniest strings to the entire cosmos. We will investigate if our world is a holographic projection and what might lurk in dimensions folded smaller than an atom. Which idea of a hidden reality sparks your curiosity the most? The first and perhaps most famous gateway into hidden dimensions is string theory. At its heart is a beautifully simple yet profound shift in how we see the building blocks of everything. Forget solid, point-like particles. Instead, picture the universe as a cosmic symphony, where every electron, every quark, every photon is a note played by an unimaginably tiny vibrating string. The pitch of the vibration, how fast or slow that string oscillates, determines what kind of particle it becomes. One note creates an electron, another a photon of light. It is a theory of pure music where matter and energy are simply different harmonies. But for this symphony to work mathematically, for the equations to balance and produce the universe we see, these strings cannot vibrate in just the 3 dimensions of space and 1 of time we experience. They need room to move. They require a stage with 10, or in some versions, 11 total dimensions. So where are the extra 6 or 7? The answer lies in a process called compactification. Imagine looking at a garden hose from a great distance. It appears as a simple one-dimensional line, but as you move closer, you see its surface is actually a 2-dimensional sheet curled into a long, thin cylinder. The extra dimension was always there, just too small to notice from afar. In string theory, the extra dimensions are thought to be curled up into fantastically complex, microscopic shapes called Calabi-Yau manifolds. Visualize them as intricate, multi-dimensional origami, folded at a scale a billion times smaller than an atom. Every point in our familiar 3-dimensional space secretly harbors one of these unimaginably small, knotted geometric shapes. The specific way these hidden dimensions are folded determines the properties of our universe, the strength of gravity, the types of particles that exist, the very laws of physics themselves. It suggests that the fundamental constants of nature are not arbitrary, but the accidental outcome of how our particular slice of reality got crumpled up. But what if our universe is not merely shaped by hidden dimensions, but is itself a kind of island within them? This is the startling vision of M-theory, a framework that unites the different versions of string theory. Here, the basic objects are not just one-dimensional strings, but also higher-dimensional membranes, or branes for short. Think of them as vast, flexible sheets of reality. Our entire cosmos, with all its galaxies, stars, and planets, could be a single 3-dimensional brane, like an immense, impossibly thin sheet of paper. This sheet does not float in empty space as we know it, but is suspended within a much larger, higher-dimensional arena called the bulk. In this picture, the particles that make up you and everything you see, electrons, quarks, photons, are like ink trapped on the surface of that paper. They are stuck to our brain and cannot leave it, but gravity is different. Gravity, according to this idea, is not made of strings confined to our brain. It is a vibration that can leak off the edge of our sheet and dissipate into the vastness of the bulk. This could be the profound answer to a long-standing mystery. Why is gravity so unimaginably weaker than the other fundamental forces? A magnet can lift a paperclip, effortlessly fighting the gravitational pull of the entire Earth. If gravity's strength is diluted because it spreads into extra dimensions, its apparent feebleness in our 3-dimensional world suddenly makes sense. The bulk is not empty, however. Drifting through it could be other branes, other entire universes with their own laws of physics, separated from us by a gap we cannot cross. We would be forever unaware of these parallel realities, floating like silent ghost ships in a higher dimensional sea. yet sometimes these sheets might touch. One compelling idea is that our Big Bang, the fiery birth of everything, was not a singularity in space, but a cataclysmic collision between our brain and another. Picture two enormous, silent sheets in a dark, higher-dimensional void, slowly drawn together until they meet. That moment of contact would release an unfathomable amount of energy, flooding our newborn brain with light and matter, setting the stage for the expanding universe we observe today. It is a creation story written not in fire but in geometry. This idea of a brain world hints at a reality where information is confined to surfaces, and that leads us to an even more mind-bending possibility. Our three-dimensional universe, with all its depth and solidity, might be nothing more than a grand illusion. It could be a hologram, not a metaphor but a literal, physical hologram projected from a flat, two-dimensional surface at the very edge of everything we know. Think of a security hologram on a credit card. That shimmering, three-dimensional image is not stored in the space above the card. All the information needed to create it is encoded on the flat, two-dimensional sticker. Our cosmos might work the same way. The information for every star, every planet, and every one of us could be written on a distant, spherical shell that surrounds us, like the information on the surface of a cosmic DVD. This is the holographic principle, and its origins are as strange as the idea itself. It began not with holograms, but with the most mysterious objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume, but to the area of its event horizon, the point of no return. This was bizarre. Entropy usually grows with volume. A messy room has more places to hide things than a messy desk, but for a black hole, the information content seemed to be painted on its surface, not stuffed inside its interior. Later, Leonard Susskind and Gerard T. Hooft took this idea and ran with it. They proposed that this was not just a quirk of black holes, but a fundamental law of the universe. The maximum amount of information that can exist in any region of space is not determined by how much you can pack into its volume, but by the area of the surface that surrounds it. It is as if the universe has a pixel limit, and those pixels are all on the walls, not filling the room. This leads to a staggering conclusion. If all the information describing the three-dimensional world inside a region is perfectly encoded on its two-dimensional boundary, then the three-dimensional world we experience might be a kind of projection, a holographic rendering of that data. Your perception of sitting in a room, of feeling the solidity of a chair, of seeing depth and distance, would be an incredibly convincing simulation generated from data on a faraway screen. So is reality an illusion, not in the philosophical sense of a dream, but in a shockingly physical one. The solidity we experience is real to us, just as the holographic eagle on a credit card looks real to our eyes. But its ultimate source, the true bedrock of reality, may exist on a flat, information-dense surface we can never see. Every event in our history, every thought you have, could be a single pixel flickering on the boundary of the cosmos. The holographic principle redefines reality as a projection, but what if every possible version of that reality actually exists? This brings us to a theory born from the bizarre heart of quantum mechanics, the many worlds interpretation. At the quantum level, particles exist in a fuzzy state of probabilities called superposition. An electron is not simply here or there, it is both places at once, a cloud of potential. Only when we observe or measure it does this cloud collapse into a single, definite outcome. But where do all those other possibilities go? The many worlds interpretation offers a radical answer: they never vanish. Instead, the universe itself splits. Every single quantum event with more than one possible outcome causes reality to branch into multiple, equally real versions. In one branch you turn left, in another you turn right. In one, a radioactive atom decays. In another, it does not. Each branch is a complete separate universe, forever unaware of the others. From this perspective, these infinite alternate realities form a new kind of hidden dimension, not a curled-up spatial dimension, but a dimension of possibility. Visualize it as an endlessly forking tree, where every twig is a full-fledged universe with its own unique history. This is not a multiverse of separate spatial branes floating in a bulk, but a multiverse of timelines splitting from a shared trunk. The philosophical implications are staggering. It means every choice you did not make, every chance event that went another way, is playing out somewhere in this vast tapestry of actuality. There is a universe where you became an astronaut, and another where dinosaurs never went extinct. The version of you reading this script is just one thread in an infinite weave. This differs profoundly from spatial extra dimensions. Those are additional directions you could theoretically move if only you were small enough. The branching dimensions of many worlds are not places you can travel to. They are narratives that have diverged. They represent the total sum of everything that could ever happen, all happening at once. While it feels like we are moving forward on a single timeline, this theory suggests we are constantly navigating a multidimensional labyrinth of our own making, with new corridors appearing with every quantum flicker. While the many worlds idea deals in branching timelines, the first serious scientific proposal for a hidden spatial dimension came from a surprising source nearly a century ago. It was the work of a relatively unknown mathematician named Theodore Kaluza. In 1919, just after Einstein published his general theory of relativity, Kaluza made a breathtaking observation. He took Einstein's equations, which describe gravity as the warping of four-dimensional spacetime, and did something simple yet audacious. He wrote them out again, but this time he assumed the universe had not four but five dimensions. The math still worked perfectly. In fact, it did more than work. When Kaluza separated out the parts of his five-dimensional equations, he found two distinct sets. One set was Einstein's original equations for gravity. The other set was none other than James Clerk Maxwell's famous equations for electromagnetism, the force governing light, electricity, and magnetism. In one elegant stroke, Kaluza seemed to have unified the two known fundamental forces of his time by adding a single unseen dimension. It was a revelation. The fifth dimension was not like the others, however. Physicist Oscar Klein later refined the idea, proposing this extra dimension was not large and expansive, but curled up into a fantastically small circle, much smaller than an atom. To understand this, picture every single point in our familiar three-dimensional space. Now, at that point, imagine attaching a tiny, invisible circle, a loop so minute that no experiment could ever probe it. An ant living on a long, thin garden hose experiences this. Along the length of the hose, it can travel a long distance, but if it walks around the circumference of the hose, it returns to its starting point almost instantly. From a distance, the circular dimension is invisible and the hose looks like a simple line. Our universe, according to Kaluza and Klein, is like that hose, but with a circular dimension curled up at every location. This tiny, cyclic dimension was the key to unification. A particle moving in this hidden circle would not appear as motion to us, but as an electric charge. The different ways a particle could vibrate or orbit within this microscopic loop would correspond to different fundamental particles in our four-dimensional world. For a moment, physics held its breath. Could all of reality be explained by geometry in a higher dimension? The theory ultimately stumbled. It could beautifully unify gravity and electromagnetism, but it could not account for the two other fundamental forces discovered later, the strong and weak nuclear forces. Furthermore, there was no experimental reason to believe in this curled-up fifth dimension. It was a magnificent mathematical idea in search of physical proof. Yet its legacy is immense. Kaluza-Klein theory was the first concrete blueprint. the original inspiration that told physicists hidden dimensions were not just science fiction, but a legitimate, even beautiful, tool for understanding the cosmos. It planted the seed that would, decades later, grow into the vast theoretical forest of string theory and brane worlds. It proved that sometimes, to solve the deepest puzzles of our universe, you must be willing to look for answers in directions you cannot see. The search for a universe without a true beginning leads us to a grand, rhythmic vision of creation. Beyond a single brane collision lies the possibility of an eternal, cosmic heartbeat known as the cyclic model. This theory proposes that our universe is not a one-time event expanding from a singular point into eventual cold emptiness. Instead, it is part of an endless, repeating cycle of birth, death, and rebirth, driven by the very geometry of hidden dimensions. The engine of this infinite cycle is the dance of two branes. Picture our three-dimensional universe as one immense, flexible sheet. Not far away in the higher dimensional bulk floats a second brane, a parallel world we might call a shadow universe. These two vast membranes are not static. They are drawn together by a force acting across the bulk, perhaps a form of higher dimensional gravity or a spring-like tension in the space between them. Over trillions of years, they slowly, inevitably approach one another. When they finally meet, the collision is not gentle. It is a cataclysm of unimaginable energy. This moment of impact is what we perceive as our Big Bang. It floods our brain with radiation and matter, setting off the expansion and the formation of galaxies, stars, and planets. But here is where the story diverges from the traditional one. After the collision, the branes do not stick together. They bounce apart, repelled by the incredible energy of their meeting. Our universe then enters its long phase of expansion and evolution, the era we are living in now. Yet the force that drew them together remains, after an almost incomprehensible span of time. As the energy of our universe spreads thin and dark energy drives continued expansion, the attraction will overcome the momentum of the bounce. The branes will begin to approach each other once more, starting the countdown to the next great collision. This elegant model solves profound puzzles. It offers a universe with no need for a mysterious starting point, no initial singularity where the laws of physics break down. Time stretches infinitely into both the past and the future, a series of cycles without beginning or end. It also provides a potential future. Instead of a cold, dark, and lonely heat death, our distant cosmic fate is a fiery rebirth. Everything we know will be swept away in the next collision, only to be rekindled in a new form in the next cycle. Each new universe inherits a faint thermal imprint from the one before, a cosmic memory carried in the background radiation. This means the cycles are not perfect copies. Each iteration may have slightly different constants, different arrangements of matter, leading to endless variation across eternity. Our existence, in this view, is just one verse in an endless cosmic poem, written and rewritten by the slow, majestic oscillation of realities in the dark. But if every universe in the cyclic model is a variation on a theme, where do those variations ultimately come from? The answer may lie in a staggering cosmic geography known as the string theory landscape. This is not a single theory, but a consequence of the mathematics of extra dimensions. Recall those intricate Calabi-Yau shapes, the six-dimensional geometries curled up at every point. It turns out there is not just one way to fold them. The number of mathematically possible configurations is astronomical, estimated to be 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it dwarfs the count of atoms in our observable universe. Each unique way of crumpling these hidden dimensions produces a distinct set of physical laws. The strength of gravity, the mass of an electron, the number of particle families, all of these fundamental constants are frozen into place by the specific geometric twist of the microscopic landscape. This means string theory does not predict one universe. It predicts a near-infinite array of them, a vast collection of every possible physics. Picture a cosmic mountain range of unimaginable scale. Each valley in this range represents a stable configuration, a pocket of reality where the dimensions have settled into a specific, self-consistent fold. Our universe is just one valley among countless others. In another valley, gravity might be 100 times stronger, causing stars to burn out in 1,000,000 years. In another, the nuclear forces might be too weak to bind protons and neutrons, so atoms never form. Most of these universes would be sterile, lifeless voids or chaotic plasmas where nothing complex could ever emerge. This leads directly to one of the most controversial ideas in modern cosmology, the anthropic principle. In its simplest form, it states that the constants of our universe appear finely tuned for life because if they were not, we would not be here to notice. We find ourselves in a universe with the right conditions for carbon-based life, not because it was designed or is statistically likely, but because it is the only kind of universe in which observers like us could possibly arise. It is a cosmic version of a survivor's bias. Imagine a puddle waking up one morning and thinking, "This hole I fit into is perfectly shaped for me. It must have been designed to hold me." The puddle does not consider that it is the water that has adapted to the shape of the hole, not the other way around. In the landscape multiverse, we are that puddle. Our universe's particular valley has the right contours for life, so here we are. This idea is deeply unsettling to many scientists, as it seems to move explanation from fundamental law to mere environmental selection. Yet it offers a potential answer to the fine-tuning problem. Why do dozens of fundamental numbers seem precariously balanced to allow galaxies, planets, and life? In an infinite landscape, every possible balance, no matter how improbable, exists somewhere. We simply inhabit one of the rare valleys where the conditions are just right. The sheer scale of the landscape multiverse is dizzying, but one specific valley within it offers a dramatic alternative to our cosmic origin story. This is the ekpyrotic universe, a model that takes the cyclic collision of branes and gives it a precise, chilling new form. The name itself comes from an ancient Greek word meaning conflagration or out of fire. Yet the process it describes begins not in heat, but in a profound and eerie cold. In this vision, our universe starts not with a hot, dense singularity, but with a slow, grinding collision between two parallel branes drifting through a higher dimensional space. These branes are not racing toward each other. They are almost stagnant, drawn together by a faint but persistent force across the bulk. Their approach is so gradual that the space on their surfaces is nearly empty, dark, and cold. There are no searing temperatures, no blinding light, just two vast, silent sheets of reality on an inevitable course. When they finally meet, the energy of their collision is not released in a single central point. Instead, it ripples across the entire surface of our brane like a shock wave. This wave of creation converts the kinetic energy of the impact into the raw heat and particles that become our Big Bang. The universe is born not from a point of infinite density, but from a plane of contact, a line of fire drawn across the void. This stands in stark contrast to the dominant theory of cosmic inflation. Inflation posits that a fraction of a second after the traditional Big Bang, our universe underwent a period of faster-than-light expansion, smoothing it out and planting the seeds for galaxies. The ekpyrotic model achieves a similar smoothing, but through the opposite mechanism, a slow, drawn-out contraction phase before the bang. As the branes approach over eons, any wrinkles or irregularities on their surfaces are stretched and flattened, like smoothing a crumpled sheet by pulling it taut from the edges. By the time of the collision, the starting conditions are exquisitely uniform. This leads to a key prediction. The cosmic microwave background, the ancient afterglow of the birth of our universe, should show a very specific pattern of temperature variations. In inflationary theory, these primordial ripples are predicted to be nearly scale invariant, meaning they look statistically similar on all size scales. The ekpyrotic model, however, predicts a slight tilt in this pattern. The ripples should be slightly stronger on larger scales than on smaller ones, a fingerprint of that long, smoothing contraction. While current observations from satellites like Planck align very well with inflation's predictions, the search for any deviation, any hint of that ekpyrotic tilt continues. It is a forensic investigation into the very first moment, seeking to determine if our universe was born from a fiery explosion or a cold, geometric kiss in the dark. The quest for a single, elegant equation that explains all of reality is the holy grail of physics. This ultimate goal is called a theory of everything, and hidden dimensions are not just a curious side effect. They are the essential key that might finally unlock it. For over a century, our understanding of the cosmos has been split into two magnificent but incompatible kingdoms. On one side, we have Einstein's general relativity, a masterpiece that describes the grand, curving geometry of space-time and the force of gravity. It explains planets, black holes, and the expansion of the universe with breathtaking beauty. On the other side, we have quantum mechanics, which governs the bizarre, probabilistic world of the very small, the forces that hold atoms together and make stars shine. These two frameworks work perfectly in their own domains, but when forced to meet, they produce nonsensical answers like infinities that break all the math. This schism is the deepest crack in our understanding of nature. The dream of a theory of everything is to heal this rift, to show that gravity and the quantum forces are not separate at all, but different faces of a single, deeper reality. And this is where extra dimensions offer a breathtaking possibility. In our familiar four dimensions, gravity is the odd one out. The other forces, electromagnetism and the strong and weak nuclear forces, are described as exchanges of quantum particles. But gravity does not fit this mold neatly. However, if we allow space-time to have more dimensions, gravity's nature changes. In the higher dimensional bulk, gravity might behave more like the other forces, its unique weakness simply a result of being diluted across directions we cannot perceive. String theory and M-theory take this idea and run with it. In those extra curled-up dimensions, the different vibrations of strings or the ways membranes intersect could generate all the particles and forces we see, including the graviton, the hypothetical quantum particle of gravity. The geometry of those hidden dimensions would dictate everything. One specific fold produces the electromagnetic force, another twist creates the strong nuclear force. Gravity emerges from the overall shape of the stage itself. In this vision, the four fundamental forces we experience are not fundamentally different. They are simply the unique notes played on the multidimensional instrument of reality, all arising from the same underlying principle. The quest for unification is driven by a deep belief in nature's elegance. Physicists are guided by the conviction that the universe at its core is not a messy patchwork of unrelated rules but a coherent, beautiful system. Finding that single framework would be one of humanity's greatest intellectual achievements, revealing that all the complexity we see, from the spin of an electron to the whirl of a galaxy, is the magnificent and inevitable consequence of geometry in a hidden, higher dimensional space. Gravity's embarrassing weakness hides a profound clue about reality's true shape. Among the fundamental forces, it is the staggering outlier. A tiny fridge magnet can lift a paperclip, defeating the gravitational pull of the entire Earth. The strong nuclear force, which binds atomic nuclei, is about 100 trillion times stronger than gravity. This is not just a difference in degree, it is a cosmic mystery begging for an explanation. The brain world model offers an elegant and startling answer. Gravity is not weak, it is merely diluted. In this picture, our entire universe is a three-dimensional membrane, or brane, floating within a vast, higher-dimensional arena called the bulk. The particles that make up you, the light you see, and the atoms in your hands are like specks of paint stuck to the surface of that membrane. They are bound to our brain and cannot leave it. Gravity, however, is different. It is not made of particles trapped on the brain. Instead, think of gravity as vibrations or ripples in the very fabric of spacetime itself. In a universe with extra dimensions, these ripples are not confined to our three-dimensional sheet. They can propagate off the brain, spreading out into the unseen bulk. Imagine you are in a small, cramped room and you turn on a powerful speaker. The sound is intense, concentrated, and loud. Now, open a door to a gigantic, empty hangar. The same sound waves now spread out into that vast new space. From your perspective in the small room, the sound becomes faint, diluted by the extra volume it has to fill. This is precisely what may be happening with gravity. The force we feel in our three-dimensional brain is just a tiny fraction of its full strength, because most of its influence is leaking away into the hidden expanse of the bulk. The other forces being stuck to our brain remain concentrated and therefore appear immensely powerful by comparison. This leakage provides a natural, geometric reason for gravity's feebleness without needing to fine-tune any numbers. It suggests that on its home turf, in the full higher dimensional space, gravity might be just as strong as the other forces. We are simply experiencing its faint shadow. This idea is not just philosophical speculation, it leads to a concrete, testable prediction. If extra dimensions exist and gravity can seep into them, then at very small distances, comparable to the size of those curled-up dimensions, gravity should suddenly become stronger. At scales larger than a millimeter, gravity perfectly follows Newton's famous inverse square law. But if you could measure the gravitational pull between two objects separated by a microscopic distance, you might detect a deviation as gravity's lines of force begin to slip into the extra-dimensional space. Scientists are conducting incredibly precise tabletop experiments to look for exactly this effect, using exquisitely sensitive pendulums or tiny, oscillating cantilevers. On an even more dramatic scale, particle colliders like the Large Hadron Collider are hunting for evidence. When protons are smashed together at nearly the speed of light, the collision energy must be conserved. But if some of that energy is carried away by particles or gravitational waves that escape into the bulk, it would appear as missing energy in our detectors, a telltale signature that something has left our brain altogether. Finding such a signal would be a direct window into the higher dimensional architecture of reality, proving that our universe is but a slice of a far grander hidden whole. Gravity's leakage into the bulk offers one solution to its weakness, but what if the extra dimensions themselves are not flat or tiny, but dramatically curved? This is the revolutionary insight of physicists Lisa Randall and Raman Sundram. Their models propose a universe where a hidden dimension is not compactified into a microscopic knot, but is instead vast and profoundly warped. Picture a long, narrow funnel or a deep, smooth throat. This is the shape of the extra dimension in their most famous model. Our familiar three-dimensional universe resides on one end of this funnel, a brane anchored at the thick, wide end. Far down the narrow throat at the other end of this warped space lies a second brane, a separate universe sometimes called the Planck brane, where gravity is naturally incredibly strong. The genius of this geometry lies in the steep gravitational gradient between them. The fabric of spacetime itself is stretched and distorted along this hidden dimension, creating an exponential drop in energy scales. A particle or force field living on our brain at the wide end would have its effective mass and energy warped down by this steep slope. This provides an elegant, geometric solution to the hierarchy problem, the puzzling gap between the immense strength of the quantum forces and the extreme weakness of gravity. In this warped throat, gravity is strong at the narrow Planck brane, but by the time its influence climbs up the steep slope to reach our brain, it has been diluted to the feeble strength we observe. All other particles and forces are confined to our brain, so they remain undiluted and appear strong. It is as if we live at the top of a deep well, hearing only the faintest echo of a powerful sound originating from the bottom. This model allows for a hidden dimension that is relatively large, perhaps even infinite in extent, yet remains hidden because only gravity can freely traverse the warped bulk. Matter and light are stuck on our membrane, so we cannot see or travel into this funnel, but gravity's whispers tell us of its shape. The Randall-Sundrum models transformed the landscape of theoretical physics by showing that extra dimensions did not have to be small to be hidden. They just had to be shaped in a way that selectively filters reality, letting only the faintest shadow of gravity slip through to our world. The profound warping of hidden dimensions could hold the key to a mystery far closer to home, the relentless forward march of time itself. Why does time only flow in one direction? We remember the past but not the future. A broken glass does not reassemble itself. This fundamental asymmetry, called the arrow of time, is one of the deepest puzzles in physics. Some theorists now propose that the answer may not lie within our four-dimensional spacetime, but in how our universe is anchored within a higher dimensional reality. The most common arrow of time is driven by entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, creating the distinction between past order and future chaos. But this raises a deeper question. Why was the entropy of the early universe so incredibly low? The Big Bang appears to have been a state of exquisite, improbable order, a wound-up spring that has been unwinding ever since. One compelling idea suggests this low entropy starting point is not an accident, but a geometric necessity dictated by our brain's existence. Imagine our three-dimensional universe as a vast sheet, but one that is dynamic like the surface of a growing bubble. In its earliest moments, this brane was tiny, smooth, and incredibly uniform. From the perspective of the higher dimensional bulk, this was a low entropy configuration because the brane itself had a very simple, minimal shape. As the brane expanded and cooled, it had more room to develop complexity wrinkles, structures like galaxies, and eventually life. The increase in entropy we experience as the arrow of time is simply the natural evolution of this membrane becoming more complex and textured within the higher dimensional space. The direction of time, then, might be aligned with the direction of our brain's expansion or evolution in the bulk. We are not moving through time so much as time is the story of our slice of reality unfolding. Another, more speculative idea connects time's arrow directly to the collision of branes in cyclic models. In each cycle, the branes approach, collide, and rebound. The moment of collision, our Big Bang, resets entropy to a low state. The subsequent expansion represents the single, coherent direction of time for that cycle, the long sigh after the cosmic collision. From our limited perspective within the brane, we can only perceive this one-way expansion, this irreversible journey from order to disorder. We cannot see the larger cyclic dance in the bulk, just as an ant on a balloon being inflated cannot perceive the balloon's eventual deflation. This suggests that the relentless forward flow we experience, the reason you cannot unbreak an egg, is not a fundamental law of the cosmos, but a local, emergent property of our particular dimensional slice. It is the shadow cast by a much larger, perhaps symmetric, higher dimensional process. If we could step outside our brane, the distinction between past and future might blur or vanish entirely, revealing time's arrow as a compelling illusion, a story written by geometry. The ghostly pull holding galaxies together might not be made of anything in our universe at all. Dark matter is the cosmic skeleton, an invisible scaffold whose gravity prevents spinning galaxies from flying apart. For decades, the hunt has focused on finding a new, exotic particle here in our dimensions. But what if we are searching in the wrong place entirely? One of the most provocative ideas emerging from brane cosmology is that dark matter is not a particle we have yet to detect, but a higher dimensional shadow. It could be the gravitational influence of ordinary matter residing on a parallel brane, just a whisper away in the bulk. Picture two immense sheets of reality, our brane and another, separated by a tiny gap in a hidden dimension. The stars, gas, and planets on that neighboring brane are made of their own ordinary matter, bound by their own physics. They are completely invisible to us because light, and every particle except gravity, is confined to its home brane. But gravity, as we have learned, can leak. The gravitational pull from all that matter on the other sheet bleeds through the bulk and into our universe. To an astronomer in our brane, a galaxy would appear to be surrounded by an enormous, invisible halo of mass tugging on its stars with relentless force. They would measure its gravitational effect, call it dark matter, and never know its true origin is a mirror cosmos shining with its own unseen light. There is another, even stranger possibility. Dark matter might not be matter at all, but a geometric artifact. The intricate curvature of the extra dimensions themselves, the specific warping of the Calabi-Yau shapes at every point, could subtly alter how gravity behaves on the large scale of galaxies. This warping would create an extra gravitational contribution that mimics the presence of extra mass. It would be as if the hidden folds of space itself have a weight, a density that tugs on the stars. In this view, dark matter is not a substance but a symptom, a fingerprint of the universe's true multidimensional shape imprinted on the rotation of every spiral galaxy. These ideas turn the mystery inside out. The hunt for dark matter particles in underground labs or with particle colliders is one of science's great quests. But if the brane world hypothesis is correct, that search, while noble, might be destined to find nothing in our dimensions, the answer would lie next door in a universe we can never see, felt only through the faintest of gravitational handshakes across the dark. Dark energy's relentless push is the greatest unsolved riddle in modern cosmology. We know the universe is not just expanding, but that expansion is speeding up, driven by a mysterious repulsive force that makes up about 70% of everything. But what is it? One of the most profound possibilities is that dark energy is not a new form of energy within our universe at all, but a direct signal from the higher dimensional architecture that contains it. Think of our universe as a bubble floating in a vast, higher dimensional ocean. That ocean is the bulk. Now, what if that bulk itself has a constant, inherent energy density, a sort of ambient pressure that fills all of that hidden space? This is the modern incarnation of Einstein's cosmological constant, a fixed energy woven into the fabric of spacetime. From our perspective, trapped on our three-dimensional brane, we cannot feel this bulk pressure directly. But its presence would shape our very reality. A positive pressure in the bulk would exert a gentle, repulsive force on our membrane, causing the space within it to stretch. This would appear to us as a constant, accelerating expansion of our entire cosmos. In this view, dark energy is not something inside the room, it is the walls of the room themselves slowly pushing outward. Another compelling theory ties dark energy to motion. Our brane may not be static in the bulk. It could be slowly drifting, rippling, or even inflating into the higher dimensional void. As it moves, it might experience a kind of friction or resistance from the bulk itself. This interaction could translate into an effective energy that drives cosmic acceleration. Picture a sheet of paper gliding slowly across a table. The contact with the table creates subtle forces on the paper. Now, imagine that paper is our entire universe and the table is the bulk. The interaction between them might manifest as the smooth, pervasive push we call dark energy. This connects directly to the infamous cosmological constant problem, which is arguably the worst theoretical prediction in the history of physics. When physicists try to calculate the expected energy of empty space from quantum fluctuations in our dimensions, the number they get is absurdly, catastrophically large, about 120 orders of magnitude too big. That is a 1 with 120 zeros after it. A universe with that much energy would have ripped itself apart instantly. The fact that our measured dark energy is so infinitesimally small, yet not zero, is a screaming clue. It suggests a near-perfect cancellation is happening, a delicate balance where the huge positive energy from quantum effects is almost exactly offset by a huge negative energy from another source. That other source could be the geometry of the extra dimensions. The specific curvature and dynamics of the hidden dimensions might generate a negative pressure that precisely tunes the cosmological constant down to the tiny positive value we observe. It is as if the hidden folds of reality are under a tremendous tension, pulling inward just enough to almost perfectly balance the explosive pressure of quantum noise, leaving behind only the faintest whisper of repulsion that we now measure. Visualize our expanding universe not as an isolated balloon inflating in nothingness, but as a growing stain on a vast, still canvas or a ripple spreading on a pond of unimaginable depth. The acceleration we see may be the gentle tug of currents in that deeper, hidden sea. The accelerating expansion of our universe might be a message from a higher dimensional sea, but what if that entire sea is not physical at all? What if the hidden dimensions we have been exploring are not curled up in space, but lines of code in a cosmic computer? This is the simulation hypothesis, a theory that takes the quest for hidden reality into a startlingly different domain. It proposes that our universe, with all its galaxies, stars, and conscious beings, is not a base reality, but an artificial construct, a simulation running on some unfathomably advanced computer. In this view, the laws of physics are not fundamental truths, but the programmed rules of the simulation, the source code of reality. The three spatial dimensions and one of time we experience are not the limits of existence, but the rendered output for our user experience. So where are the extra dimensions? They could be the underlying programming variables, the mathematical scaffolding and unused processing power that exist outside our perceived reality to keep the simulation stable and consistent. Philosopher Nick Bostrom formalized this idea with a compelling trilemma. He argued that at least one of three propositions must be true. First, almost all civilizations at our level go extinct before becoming technologically mature. Second, almost all mature civilizations lose interest in creating detailed simulations of their ancestors. Or third, we are almost certainly living in a simulation. The logic is simple. If even one civilization survives to a post-human stage and retains an interest in its history, it would have the computational power to run vast numbers of highly detailed ancestor simulations. The number of simulated minds would quickly dwarf the number of original biological ones. Therefore, statistically, any randomly selected conscious being, like you or me, is far more likely to be in a simulation than in the original reality. This idea resonates eerily with the holographic principle we discussed earlier. In both cases, our three-dimensional world is not the primary reality, but a projection from a more fundamental, lower-dimensional source. For the holographic principle, that source is a two-dimensional boundary encoded with information. For the simulation hypothesis, that source is a digital substrate running an algorithm. The hidden dimensions of string theory could be seen as the complex data structures required to compute the various forces and particles, while the brane world might resemble separate server instances or simulation layers. Could we ever find evidence of this? Proponents suggest looking for possible shortcuts or optimizations in the code, what we might perceive as glitches in the matrix. These could be fundamental limits or constants that seem oddly round or simplified, like the speed of light being a nice, clean number, perhaps because it is a system constant set for processing efficiency. Some have even suggested that quantum indeterminacy, where particles exist in a haze of probability until observed, might be a rendering optimization. Why calculate the precise state of every particle in a distant galaxy if no one is looking? The program only resolves the details when a conscious observer makes a measurement, saving immense computational resources. This is a profoundly unsettling idea. It challenges the very nature of existence, suggesting that the solidity of the world and the continuity of our memories are as real as the graphics in an open-world video game, convincing and self-consistent within the rules, but ultimately just information. Yet it also offers a strange kind of hope. If our reality is a simulation, then the ultimate hidden dimensions are not spatial, but logical. The deepest secrets of the cosmos would not be found in a particle collider, but in deciphering the source code, looking for the comments left by the programmer, or finding a way to peer into the machine that runs it all. The simulation hypothesis suggests our reality might be a construct of logic and code. But what if the most intimate part of that reality, your own conscious experience, is also a clue to the universe's hidden architecture? This leads us to one of the most profound and speculative frontiers, the idea that consciousness itself might be a higher dimensional phenomenon. The so-called hard problem of consciousness, articulated by philosopher David Chalmers, asks a deceptively simple question: why do we have inner, subjective experiences at all? Why does the processing of light by our eyes and brain produce the vivid, private sensation of the color red, or the feeling of warmth? Physical science can describe the neural correlates, the brain activity that accompanies these experiences, but it struggles to explain how and why objective electrical signals give rise to subjective inner life. Some theorists propose that this gap exists because we are looking in the wrong place, or rather, in the wrong number of dimensions. What if consciousness is not generated by the brain, but is instead a fundamental feature of the cosmos, like space, time, or mass? This view, known as panpsychism, suggests that some form of rudimentary experience exists at all levels of reality. An electron might possess an infinitesimal glimmer of proto-consciousness. In this framework, the complex consciousness of a human being emerges when vast networks of these simple elements integrate in specific, highly organized ways. But where do the hidden dimensions come in? Integrated information theory, developed by neuroscientist Giulio Tononi, offers a mathematical approach. It proposes that consciousness corresponds to a system's capacity for integrated information, represented by the Greek letter phi. A system with high phi, like a human brain, has a rich, unified experience. A system with low or zero phi, like a rock or a simple computer chip, has little to none. Crucially, the mathematics of integration suggests the shape of consciousness might exist in a space with more dimensions than our physical world. Think of it this way: your brain contains nearly 100 billion neurons, each connected to thousands of others. The state of your consciousness at any single moment, all your thoughts, feelings, and sensations, is not just a list of which neurons are firing. It is the specific, intricate pattern of how all that information is woven together into a single, unified whole. That pattern of relationships, the tapestry of connections, cannot be fully mapped in three-dimensional space. It requires a kind of abstract, multidimensional space to represent all the possible ways information could be integrated. In this view, your mind is not located just inside your skull. It is a complex, high-dimensional shape, a kind of invisible geometry of information that is anchored to your brain but extends into a realm of pure relation. Your subjective experience of seeing a sunset is the brain's physical interaction with light, but the feeling of awe, the memory it triggers, the sense of beauty, that is the multidimensional shape of integrated information coming to life. This is a radical departure from seeing consciousness as a mere byproduct. Instead, it becomes a primary aspect of reality, perhaps even the reason hidden dimensions exist in the first place. Could the curled-up Calabi-Yau shapes of string theory not just dictate particles and forces, but also the fundamental substrate from which experience emerges? It is a breathtaking thought that the universe's hidden dimensions are not just for gravity or strings, but are the native home of mind itself, with our individual awareness being a localized knot in this vast thinking fabric of reality. If consciousness is a geometry woven from reality's hidden fabric, then what is the fabric itself? The mathematical universe hypothesis proposed by physicist Max Tegmark offers a breathtakingly simple and radical answer. Reality is not just described by mathematics, it is mathematics. Every mathematically consistent structure, every possible set of equations and geometric forms exists as a physical universe somewhere. This is Tegmark's Level 4 multiverse, the ultimate and final frontier of hidden dimensions. In this view, the familiar 4 dimensions of space-time, or the 10 dimensions of string theory, are not special. They are merely one particular mathematical structure that happens to contain self-aware substructures like us. Our universe is one equation among an infinite library of equations, all of them equally real. Think of a simple geometric shape like a perfect infinite plane. That two-dimensional grid is a mathematically consistent structure. According to this hypothesis, it physically exists as a universe, a vast, flat world where two-dimensional beings might live out their lives, completely unaware of our three-dimensional space. Now consider a universe governed by the rules of chess, or one built from fractal patterns, or one with 15 spatial dimensions curled into a hyper-dodecahedron. If a system of relationships can be defined without logical contradiction, it is out there, a cosmos in its own right. The hidden dimensions we have been exploring throughout this script are not merely extra spatial directions folded away in our particular cosmos. They represent the infinite variety of all possible mathematical spaces, the overwhelming majority of which we do not and cannot inhabit. Our quest to understand our own universe's 6 hidden curled dimensions is just a local investigation within one peculiar mathematical neighborhood. In the Level 4 multiverse, every possible physical law is realized somewhere. There are universes where gravity is repulsive, where time runs backward, where the number pi is exactly 3, and where the concept of dimension itself is something we could never comprehend. This idea pushes the Copernican principle to its absolute limit. We are not at the center of the solar system, our galaxy, or even our own universe. Tegmark suggests we are not at the center of mathematical existence either. Our universe's laws are not fine-tuned for life. They are simply the laws of the one mathematical structure that contains us. We find ourselves here for the same reason a fish finds itself in water. It is the only environment where a creature like it could arise. This hypothesis dissolves the boundary between the abstract and the concrete. A mathematician proving a theorem is not just exploring an ideal world of forms, they are taking a survey of a real physical cosmos. The discovery of a new geometric shape is the discovery of a new universe. It raises a profound question: what does it mean for something to exist? For Tegmark, physical existence and mathematical existence are one and the same. The multiverse is not a collection of bubbles in a higher dimensional space, but a timeless, placeless collection of all possible self-consistent structures. It is the ultimate hidden reality, not behind a curtain of space, but behind the curtain of our own assumptions about what is real. The mathematical universe hypothesis dissolves reality into pure abstraction, but our most immediate experience of existence is one of relentless change. This brings us to a hidden dimension so familiar we often forget it is one: time itself. In the early 20th century, Albert Einstein, with crucial insights from his former teacher Hermann Minkowski, performed a revolution in thought. They did not just add time to the list of dimensions, they fused it with space into a single, inseparable entity called space-time. In this four-dimensional continuum, time is not a universal ticker tape running in the background. It is a direction you can move in, just like forward, left, or up, but with a profound and strange difference. This difference is called the signature. In our three spatial dimensions, distances are measured with a positive sign. If you move 2 meters north and 2 meters east, your total spatial displacement is calculated with simple addition. But in space-time, the interval that remains constant for all observers mixes space and time with a minus sign. This subtle mathematical quirk is the reason you cannot turn around in time as easily as you can in space. It creates the immutable speed limit of light and dictates the flow of causality. Minkowski gave us a powerful tool to visualize this, the space-time diagram. Picture a graph where the horizontal axis represents space, say the distance along a road, and the vertical axis represents time flowing upward. A particle at rest is not a dot, but a vertical line, a world line, tracing its existence through time. A particle moving at constant speed becomes a slanted line. The path of a light beam, the ultimate speed limit, forms a diagonal line at a fixed angle, creating a light cone that emanates from every event. Your present moment is a single point on this diagram. Your future is not ahead of you in space, but inside the upward opening cone. From that point, the region of space-time that light from your present can eventually reach. Your past is the downward cone from which light could have reached you. Everything outside those cones is elsewhere, forever separated from you by the laws of causality. This geometry explains the mind-bending effects of relativity. Time dilation occurs when two observers move relative to each other. On a space-time diagram, their paths are slanted in different directions. Because the space-time interval must remain constant, their measurements of time and space along their respective world lines must differ. An astronaut traveling at near light speed to a distant star traces a sharply slanted world line. From our nearly vertical perspective on Earth, less time ticks along their slanted path than along our own. They age slower. There is no single now that spreads across the universe. Your now is a slice through space-time that is tilted relative to mine if we are moving. Two events that are simultaneous for you may happen at different times for me. This shatters the Newtonian idea of absolute time and space, revealing a dynamic, interwoven fabric where our separation in time is as real and tangible as our separation in space. We are all travelers navigating this four-dimensional landscape, our world lines weaving an unchangeable history from the past toward the future, guided by the fixed geometry of light cones. This classical unification was the first crack in the door, showing physicists that dimensions could blend in non-intuitive ways and that our perception is but a shadow of a higher dimensional truth. Einstein and Minkowski fused time with space, but what if there are more spatial dimensions beyond the three we move through? This brings us to the concept of a true fifth dimension, not of time but of pure space. To grasp this, we must first try to visualize the fourth spatial dimension, a direction perpendicular to left-right, forward-back, and up-down. It is a direction we cannot point to, but one whose shadows we can draw. The classic tool for this is the tesseract or hypercube. Start with a point in 0 dimensions, extend it in one direction, and you get a line. Take that line and extend it in a perpendicular direction, and you get a square. Take that square and extend it into a third perpendicular direction, and you get a cube. Now, take that cube and extend it into a fourth perpendicular direction. The object you create is a tesseract. We cannot see it fully, just as a two-dimensional being living on a flat sheet of paper could never see the entirety of a cube. They would only see cross-sections. When a cube passes through their flat world, they would see a square that appears, changes size, and then disappears. In the same way, if a tesseract passed through our three-dimensional space, we would see a cube that mysteriously appears, morphs, and vanishes. An animated unfolding of a tesseract is a mesmerizing glimpse into this higher geometry. Just as you can unfold a cube into a flat, two-dimensional cross of 6 squares, you can unfold a tesseract into a three-dimensional cross of 8 cubes. It is a shape that exists fully only in a space with 4 spatial dimensions. Now, consider the powers of a being who lived in such a 4-dimensional space. To them, our three-dimensional world would be utterly transparent. They could look directly at you and see not just your skin, but your beating heart, your brain, your bones, all at once, just as we can look at a drawing on paper and see everything inside the square's boundary without opening anything. They could remove an object from a sealed, locked safe without ever touching the walls, simply by lifting it into the fourth dimension and placing it back down outside. Our entire universe would be like a page in a book to them, and they could turn to the next page. If such a fifth spatial dimension exists and is large enough to traverse, the implications for travel are staggering. A wormhole, often pictured as a tunnel connecting two distant parts of space, might not be a tunnel through our three dimensions at all. It could be a shortcut that goes through this higher dimension. Picture two dots on opposite ends of a piece of paper. The distance along the sheet is long, but if you fold the paper so the dots touch, you create a shortcut through the third dimension. In the same way, if our three-dimensional space is a membrane that can be curved through a fourth spatial dimension, 2 points billions of light years apart could be brought next to each other. A ship would not need to travel the long way through our space. It could dip into the higher dimension and re-emerge almost instantly elsewhere. This is not magic, it is geometry in a universe with one more direction to move than we can perceive. The Tesseract is more than a mathematical curiosity. It is a keyhole, offering a fleeting shadow of a reality where distance is an illusion and every secret is laid bare. A tesseract hints at shortcuts through higher dimensions, but the most famous proposal for such a bridge is the wormhole. Known in physics as an Einstein-Rosen bridge, a wormhole is not a tunnel dug through space, but a structure woven from the very fabric of spacetime itself. Picture the universe as a vast, two-dimensional sheet. If you want to travel from one side to the other, the journey across the sheet is immense. But if you could fold the sheet, bringing those two distant points to touch, you could create a shortcut, a tunnel connecting them. In our three-dimensional reality, this tunnel would be a sphere, a throat connecting one region of space to another. You would not travel the long way around. You would step into the sphere and emerge almost instantly, light years away. The mathematics for such a structure emerged directly from Einstein's equations of general relativity. In 1935, Albert Einstein and his colleague Nathan Rosen explored the idea that what we perceive as a particle, like an electron, might be the mouth of a microscopic bridge connecting to another part of the cosmos. This was not science fiction, but a serious, if speculative, investigation into the geometry of reality. For a wormhole to be traversable, however, it must be held open against its own fierce desire to collapse. The immense gravity at the tunnel's narrowest point, the throat, would snap it shut in an instant, crushing anything attempting to pass through. To prevent this, physicists have proposed the need for a bizarre substance known as exotic matter. This is not antimatter or dark matter, but something with even stranger properties, negative energy density. Think of it as a kind of anti-gravity. Where normal matter creates attractive gravity, curving spacetime inward, exotic matter would create a repulsive effect, propping the throat of the wormhole open like a scaffold against the crushing weight. While tiny amounts of negative energy might be possible through quantum effects, the quantities needed to stabilize a human-sized wormhole are far beyond anything we can conceive of creating. The implications of a stable wormhole stretch beyond mere travel. Because spacetime is a unified fabric, a wormhole could connect not just two places but two times. If one mouth of the wormhole were taken on a journey at near light speed while the other remained stationary, time would pass slower for the moving mouth due to relativity. Upon returning, the moving mouth might be only a few years older, while the stationary one could be centuries older. Stepping through from the older side would, in effect, be a journey into the past of the other location. This creates the potential for a time machine, raising all the famous paradoxes, like going back and preventing your own birth. Most physicists believe nature has a law, a cosmic censorship, that prevents such paradoxes, perhaps by making wormholes violently unstable the moment they are configured for time travel. Iconic visualizations in films often show a wormhole as a shimmering tunnel of stretched starlight. A more accurate depiction, grounded in brain world ideas, might show our universe as a flat sheet. The wormhole would not be a tunnel through the sheet, but a shortcut that arcs up and away from it, passing through the higher dimensional bulk before diving back down to another point. From within our dimensions, it would appear as a spherical portal. From outside, it would look like two distant points of our reality connected by a thread in the dark. These bridges remain firmly in the realm of theory, magnificent possibilities carved from the equations of gravity, waiting for a universe strange enough to build them. While wormholes offer hypothetical shortcuts, their opposite end might be something even more spectacular. A white hole is the theoretical reverse of a black hole, a region of space-time where nothing can enter, but matter and energy can only erupt. If a black hole is a cosmic drain from which nothing returns, a white hole is a fountain spewing light and matter outward with irresistible force. The mathematics of general relativity allows for such an object just as easily as it allows for black holes, yet we have never observed one. This is likely because white holes are profoundly unstable. Imagine trying to hold a geyser underground, forcing all that pressurized water back down. The system would violently explode. In the same way, any ordinary matter or energy falling onto a white hole's boundary would disrupt it, causing the entire structure to collapse. So if they cannot exist for long in our universe, what purpose could they serve? One compelling idea is that a white hole is not a standalone object but one end of a wormhole. The black hole is the entrance, the point of no return. The white hole is the exit, the point of no entry, erupting into another region of space-time. In this view, the wormhole is the tunnel connecting the two. An object falling into the black hole might, in theory, be expelled from the white hole, perhaps in a different time or even a different universe entirely. This connects directly to the brain world models we explored earlier. A wormhole threading through the bulk could connect two separate branes. The black hole mouth resides in our universe, while the white hole exit erupts onto a parallel brane. From the perspective of that other universe, the sudden, violent appearance of energy and matter from a single point would look like a spontaneous creation event, a miniature Big Bang. This leads to a staggering cosmological idea. What if our own Big Bang was a white hole, not from a wormhole within our universe, but from a connection to something else entirely? Picture our entire cosmos as the erupting output of a white hole in a parent universe. All the energy, all the space-time that makes up everything we see, could have fountained out from this singular event in a higher dimensional reality. This would mean our universe is not isolated, but is connected through a one-way passage to a grander cosmic structure. We are not the source, but the result, the aftermath of a dimensional rupture. Visualize it not as an explosion in empty space, but as a continuous unfurling, a fountain of reality itself pouring into existence from a single, timeless point. While such an object would be fleeting, its legacy would be everything. The search for evidence is a search for anomalies in the very early universe, patterns in the cosmic microwave background that suggest a directional origin, a preferred point from which everything flowed. Finding such a fingerprint would mean our entire history is the echo of a shout from another dimension. Two particles born together can remain forever linked, no matter how far apart they fly. This is quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles are entangled, measuring the property of one, like its spin or polarization, instantly determines the state of the other. This connection appears to happen faster than light, seemingly violating the cosmic speed limit and our intuitive sense of locality, the idea that objects are only influenced by their immediate surroundings. So how can one particle know what happens to its partner across the galaxy? One radical explanation suggests they are not communicating through our space at all, but are connected through a shortcut in a hidden dimension. Picture our three-dimensional universe as the vast surface of an ocean. Two entangled particles are like buoys floating on that surface, separated by thousands of miles of water. If they were only connected through the ocean's surface, a signal between them would have to travel that immense distance. But what if a rope connects them not across the water, but through the depths below? That rope is a shortcut through a higher dimensional bulk. From the perspective of the surface, the buoys are far apart. From the perspective of the bulk, they are neighbors, tied together by a thread that bypasses the conventional geometry entirely. This idea was given profound weight by a conjecture known as ER equals EPR, proposed by physicists Juan Maldeisner and Leonard Susskind. They suggested that the mysterious connection of quantum entanglement, EPR, might be physically equivalent to a microscopic wormhole, an Einstein-Rosen bridge or ER. In this view, two entangled particles are not truly separate. They are connected by a Planck-scale wormhole, a tunnel through the higher dimensional fabric of spacetime so tiny it is unfathomable. The entanglement is the quantum signature of this geometric bridge. When you measure one particle, you are not sending a signal to the other. You are affecting a single, connected entity that stretches across a hidden dimension. The information was already shared through the shortcut, so no faster than light travel in our three-dimensional space is required. This transforms our understanding of the quantum world. The void between particles might not be empty. It could be threaded with an invisible web of these wormhole connections, a subspatial network that ties the universe together at its most fundamental level. Entanglement would then be the footprint of a deeper geometric reality, where what we perceive as separate objects are just distant ends of a single, convoluted shape in a higher dimensional space. The spooky action is not action at all, but a revelation of a hidden unity, a reminder that the true map of reality may be drawn with lines we cannot see. The spooky connection of entangled particles hints at a hidden geometry, but the universe may have been woven from an even more spectacular process. This is cosmic inflation, a theory proposing that a fraction of a second after the beginning, our entire cosmos underwent a period of exponential, faster-than-light expansion. For a fleeting moment, the fabric of spacetime itself stretched at an unimaginable rate, smoothing the universe to an incredible flatness and planting the seeds for all future galaxies. But this theory does more than explain our universe's smoothness. It predicts the existence of countless others. The mechanism driving inflation is thought to be a quantum field, often called the inflaton field. Picture this field as a vast, sloping energy landscape, like a mountain covered in fresh snow. At the very top, the field holds immense potential energy, and this energy causes space to inflate at a staggering pace. This is the false vacuum state, an unstable but powerful configuration. Like a ball perched on the peak, the inflaton field eventually wants to roll down the slope. When it does, it settles into a lower energy valley, a true vacuum. The energy released in this roll down heats the universe, creating the hot soup of particles of the traditional Big Bang. But here is where the magic happens. According to quantum physics, this roll down does not happen everywhere at once. In some regions of the inflating space, random quantum fluctuations cause the inflaton field to lose its energy and settle down early. In other regions, it keeps holding on, continuing to inflate at an exponential rate. Imagine a pot of water just beginning to boil. Bubbles of steam form at random points on the bottom. Each bubble is a region where the water has transitioned to a new state, steam, while the surrounding liquid water continues to boil furiously. Now, let that pot be infinitely large and let the boiling go on forever. Cosmic inflation works the same way. Our observable universe is inside one such bubble, a region where inflation stopped about 13.8 billion years ago. Outside our bubble, the inflating spacetime continues to expand at a mind-numbing speed, far faster than light can travel across it. In that eternally inflating background, new bubbles are constantly forming, each one a separate universe with its own Big Bang. This is the inflationary multiverse, a boundless, frothing sea of cosmic foam where new universes nucleate without end. Each bubble universe could be radically different from our own. When the inflattened field settles into its low-energy state in a given bubble, it freezes the laws of physics for that region. The specific valley it lands in determines the constants of nature, the number of spatial dimensions that become large and stable, and the types of particles that exist. In one bubble, 6 spatial dimensions might have uncurled, creating a universe of impossible geometry. In another, the strength of the nuclear force might be too weak for atoms to form, leaving a dark, empty cosmos. Our universe is simply one bubble among an infinite number, a single accidental garden in a wilderness of every possible physics. We are not the center of this multiverse, we are not even special. We are just fortunate inhabitants of a bubble where the numbers allowed stars, planets, and life to emerge. The stunning vista of the inflationary multiverse suggests that every possible reality, no matter how strange or barren, exists somewhere in that eternal, bubbling expanse, forever out of reach beyond the impenetrable wall of our own expanding sky. The serene geometry of black holes hides a searing contradiction at its very edge. This is the firewall paradox, a modern crisis that threatens to rewrite our understanding of gravity, quantum mechanics, and reality itself. It all begins with a simple, profound fact: information cannot be destroyed. In quantum theory, the complete history of every particle that falls into a black hole, its type, its spin, its energy, must be preserved in some form. Yet, according to classical general relativity, once something crosses the event horizon, it is lost forever, its information seemingly crushed into the singularity. For decades, Stephen Hawking proposed a way out. He showed that black holes are not completely black. They slowly evaporate by emitting a faint glow of radiation from just outside their event horizons. This Hawking radiation carries away energy, causing the black hole to shrink and eventually vanish. But here lies the paradox: Hawking radiation is random thermal noise. It contains no specific information about what fell in. So, when the black hole finally evaporates, all the detailed information about the stars, planets, or spaceships it consumed appears to be lost forever, violating a core tenet of quantum physics. This is the black hole information paradox. To resolve it, physicists explored a shocking possibility. What if the information is not lost inside, but is somehow encoded in the Hawking radiation as it leaks out? For this to work, the radiation emitted near the end of the black hole's life must be subtly entangled with radiation emitted much earlier. But there is a devastating catch. For the information to escape, this late-time radiation must also become entangled with particles that fell into the black hole long ago. In quantum mechanics, a particle cannot be fully entangled with 2 different systems at once. This is the law of monogamy of entanglement. If the outgoing radiation is entangled with the early radiation to carry information, it must break its entanglement with the particles inside the horizon. Severing quantum entanglement is not a gentle process. It releases a catastrophic amount of energy. The result, according to a landmark paper in 2012, would be a wall of searing, high-energy particles, a firewall right at the event horizon. This is not a metaphorical wall. It is a literal curtain of destruction, a boundary of unimaginable heat that would incinerate anything attempting to cross. This presents an impossible choice. Either general relativity is wrong, and the event horizon is not a smooth, uneventful place as Einstein predicted, or quantum mechanics is wrong and information is truly destroyed. Both options are deeply unsettling. The firewall paradox forces physicists to question the nature of the event horizon itself. One leading escape route returns us to the holographic principle. If our 3-dimensional view of the black hole interior is an illusion, and all the information is actually stored on its two-dimensional event horizon, then nothing ever truly falls into a three-dimensional pit. From the perspective of the information, it is simply scrambled onto a vast, hot surface. The falling astronaut would not experience a firewall because, in the holographic description, there is no inside to fall into in the traditional sense. The three-dimensional journey is a projected story, while the fundamental reality is the chaotic, two-dimensional data on the shell. The firewall might be a signal that we are trying to force a three-dimensional narrative onto a fundamentally two-dimensional process. It is a sign that our intuition about space and dimensionality breaks down at the most extreme thresholds. Visualize a black hole not as a dark pit, but as a shimmering holographic sphere. The event horizon is not a gateway to another place, but the entirety of the black hole's reality, a frenzied screen encoding every bit of information that ever approached it. The fiery paradox at its edge may be the universe's way of telling us we are looking at the wrong dimension entirely. The search for a firewall's resolution leads us to a theory of perfect hidden symmetry. For every particle that makes up our world, there could be a secret twin. This is supersymmetry, a concept so elegant it feels like nature's signature. It proposes that the fundamental forces and the particles of matter are not separate categories, but two faces of a single, deeper truth. In this symmetrical universe, every known particle has a superpartner, often called a sparticle. For every quark, there is a squark. For every electron, a selectron. For the photon, there is the photino. These sparticles are not merely copies, they are reflections across a quantum divide. The particles we know, like electrons and quarks, are fermions. They are the building blocks of matter, and they hate to be in the same state, which is why matter is solid and occupies space. Their superpartners would be bosons, the force carriers like photons and gluons. Bosons love to congregate, to pile into the same state, which is how forces transmit their influence. Supersymmetry says these two families are linked. A fermion can transform into its bosonic partner, and vice versa, through a symmetry operation that exists in a more abstract space than our familiar dimensions. This is not a spatial symmetry like a mirror reflection, but a symmetry between the very categories of reality. Why does this matter for hidden dimensions? Supersymmetry is not just a nice idea, it is a mathematical necessity for the most promising versions of string theory. The vibrating strings that create our universe require supersymmetry to be stable and consistent in 10 or 11 dimensions. Without it, the equations of string theory produce nonsense, like probabilities greater than 1 or faster than light tachyons. Supersymmetry tames the wild quantum fluctuations, allowing the elegant geometry of extra dimensions to make sense. It is the glue that holds the higher dimensional edifice together. The hunt for these sparticles is therefore an indirect hunt for the hidden architecture of reality. If supersymmetry is true, then every time we smash protons together at the Large Hadron Collider, there is a chance we are not just creating known particles, but also producing their superpartners. Because sparticles are heavier than their ordinary twins, they would decay almost instantly into the particles we can detect. The signature would be a dramatic imbalance, a large amount of missing energy carried away by the lightest sparticle, which could be stable and invisible, a perfect candidate for the mysterious dark matter that holds galaxies together. Finding even one sparticle would be a revolution. It would confirm a symmetry woven into the fabric of the cosmos at a level we cannot see, providing the strongest indirect evidence yet that string theory is on the right track and that the extra dimensions it requires are more than just a beautiful fantasy. It would mean our universe is fundamentally balanced, with a hidden twin for every speck of matter, a silent partner for every force, echoing in the chambers of a reality with more room than we ever dreamed. A vacuum is not empty. Between the stars, in the deepest voids of space, the fabric of reality itself is alive with a seething quantum froth. virtual particles wink in and out of existence, borrowing energy from nothingness for the briefest instant before vanishing. This ceaseless activity gives the vacuum a baseline energy, the zero-point energy, a hum that permeates all of existence. And in 1948, a Dutch physicist named Hendrik Casimir predicted a stunning consequence of this quantum hum. He imagined two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum, parallel to each other. In the vast sea of quantum fluctuations, only certain wavelengths of virtual particles can exist between the plates. The plates act like walls, restricting which waves can fit. Outside the plates, however, all wavelengths are possible. This creates a pressure imbalance, with more possible particle fluctuations pushing from the outside than from the inside. The plates experience a tiny, irresistible force pushing them together. This is the Casimir effect. It was experimentally confirmed decades later, and today it is a standard demonstration of quantum field theory's strange predictions. But this ghostly force may be more than a quantum curiosity. It could be a direct probe into the geometry of hidden dimensions. The zero-point energy, the strength of that quantum hum, is not a fixed number. It depends on the shape and size of space itself. In a universe with extra, curled-up dimensions, the allowed wavelengths of virtual particles would be different. They would have more ways to vibrate, more modes of existence within those microscopic folded spaces. This would alter the total vacuum energy density. The Casimir effect is exquisitely sensitive to this. If extra dimensions exist, their specific geometry would change the precise force measured between the plates in a vacuum chamber. Scientists are now conducting experiments of breathtaking precision to hunt for this signature. They use not just flat plates, but intricate microscopic spheres and surfaces, measuring the forces between them at distances smaller than 1/1000th of the width of a human hair. They are looking for any deviation from the force predicted by standard three-dimensional quantum theory. A mismatch could be the fingerprint of a hidden dimension, a whisper from the Calabi-Yau manifolds curling up at every point, subtly changing the quantum chorus of empty space. Imagine those two metal plates in their dark, cold chamber. As they are drawn together by an invisible sea of ghostly particles, they are not just confirming quantum mechanics. They are acting as the most sensitive rulers ever conceived, measuring not just the gap between themselves, but the possibility that our entire universe is nestled within a larger, unseen geometry. The push you measure between two plates could one day tell us the shape of reality. The Casimir effect measures the whispers of empty space, but the shape of that silence is everything. The hidden dimensions required by string theory are not simple loops or flat planes. They are folded into breathtakingly intricate, six-dimensional sculptures known as Calabi-Yau manifolds. These are the master keys to our universe, the geometric lock that determines every physical law we experience. To understand them, we must first let go of our three-dimensional intuition. A Calabi-Yau manifold is a shape that exists in 6 compactified spatial dimensions, curled up at a scale a billion times smaller than an atom. We cannot see them directly, but mathematicians and artists can create stunning three-dimensional shadows, cross-sections of these higher dimensional objects. These projections look like impossibly complex knots, woven lattices, or delicate, multi-holed sculptures that seem to twist in on themselves forever. Each hole, each tunnel, each curve in this microscopic origami has a profound consequence. The specific way these 6 dimensions are folded dictates the vibrational patterns of the strings that lie within them. Think of a Calabi-Yau manifold as the body of a cosmic violin. Its shape determines which notes can be played. One specific resonant frequency on this geometric instrument might correspond to an electron, another to a quark, another to a photon of light. The number of holes in the manifold, a property called topology, directly influences how many families of particles exist. Our universe has three families of matter particles, like the electron and its heavier cousins, the muon and tau. This three is not an accident in this framework. It is a direct output of the Calabi-Yau shape that underpins our reality. Even the forces themselves are born from this geometry. The different ways strings can wrap around the holes and tunnels of the manifold generate the various force-carrying particles. One type of wrapping might produce the gluon that binds atomic nuclei, while another produces the photon of electromagnetism. The strength of these forces, the masses of the particles, the very existence of the Higgs boson, all of these fundamental features are frozen into place by the specific, frozen geometry of this six-dimensional knot. This means our entire cosmos, with its specific, seemingly arbitrary constants, is like a single snowflake that crystallized in a particular way from a near-infinite ocean of possibilities. Another Calabi-Yau shape with a different pattern of holes and curves would have produced a universe with four particle families, or where gravity is 100 times stronger, or where atoms could never form. The quiet, stable universe we inhabit is the direct and unique echo of one particular, exquisite hum resonating through a hidden, six-dimensional chamber. The intricate geometry of Calabi-Yau shapes suggests our universe is but one possible fold, yet its most obvious feature is a profound mystery in itself. Why are there three, not just three particle families, but three large, expanding spatial dimensions that define our entire experience of reality? This is not a trivial question. The number of spatial dimensions could have been different. String theory allows for many, but only three became macroscopic. Why did the universe choose this specific configuration? One compelling answer comes from the anthropic principle, applied directly to dimensionality itself. It posits that we observe three large spatial dimensions because this number is a prerequisite for the existence of complex observers like us. In a universe with a different number of stable, large dimensions, physics might be too barren or too chaotic for life to ever take root. Consider a universe with only two large spatial dimensions. In such a flatland, physics would be severely limited. The force of gravity, for instance, would behave very differently. In three dimensions, gravity weakens with the square of the distance. In two dimensions, it would weaken more slowly, simply with the distance itself. This has catastrophic consequences for structure. A stable, bound solar system with planets orbiting a star in neat ellipses is likely impossible in two dimensions. Orbits would be unstable. Any slight perturbation would send a planet spiraling into its sun or flying off into the void. There would be no gentle, periodic motion to allow for stable climates and seasons. Furthermore, the complexity of life itself is constrained in two dimensions. Imagine a two-dimensional digestive system. A tube running from mouth to anus would completely divide the creature into two separate pieces. Neural networks would be incredibly simple, with severe limitations on how many connections can be made without wires crossing and short-circuiting. The richness and interconnectivity needed for a complex brain may be geometrically forbidden. A two-dimensional universe might be a place of beautiful, flat patterns, but likely too simple to host the intricate machinery of life. Now consider the opposite extreme, a universe with four large spatial dimensions. Here, the problem is not simplicity, but overwhelming instability. In four spatial dimensions, the inverse square law of gravity becomes an inverse cube law. Gravity would weaken so rapidly with distance that forming large, gravitationally bound structures like galaxies and stars might be impossible. A star's gravity would struggle to hold onto its outer layers, and planets would have no stable orbital path. The equations governing motion show that in four dimensions, orbits are not closed ellipses. A planet would trace a complex, rosette-like pattern, inevitably either crashing into its star or escaping its grip after a few chaotic loops. Long-term stability vanishes. Even the atomic scale is threatened. The structure of atoms relies on the balance between electromagnetic forces and quantum mechanics. In 4 dimensions, the electron orbitals around a nucleus become unstable. An electron would either fall into the nucleus or drift away, preventing the formation of stable atoms, the very building blocks of matter. A 4-dimensional universe might be a turbulent, short-lived place where nothing can hold together long enough to form complex chemistry, let alone planets and life. 3 dimensions, it seems, is the cosmic sweet spot. It is the Goldilocks zone for dimensionality. Gravity weakens just enough to allow for vast, stable orbits over cosmic timescales, yet remains strong enough to pull matter together into galaxies and stars. Electromagnetic forces allow for stable atoms and complex molecular bonds. The geometry permits intricate, interconnected systems like circulatory systems and neural networks that are not possible in 2 dimensions, while avoiding the chaotic orbital instabilities of 4. We are not here to observe 3 dimensions because it is special in an absolute sense. We are here because 3 dimensions is one of the very few possible settings where the physics allows for stars that burn for billions of years, planets with stable orbits, atoms that bond into molecules, and ultimately, observers complex enough to ask the question. In the vast landscape of possible universes, most are silent, empty, or fleeting. Our 3-dimensional experience is not a cosmic accident, but a signature of the narrow conditions that allow a universe to become aware of itself. The 3 dimensions we inhabit may be a cosmic necessity for life, but proving the existence of any others requires more than elegant reasoning. It demands evidence. Deep beneath the French-Swiss border, in a circular tunnel 27 kilometers long, the world's most powerful microscope is hunting for that proof. The Large Hadron Collider does not magnify objects with lenses. It smashes protons together at nearly the speed of light, recreating conditions not seen since the first fraction of a second after the Big Bang. In the fiery aftermath of these collisions, physicists sift through the debris, searching for anomalies that could shatter our 3-dimensional worldview. One of the most sought-after signatures is missing energy. According to the law of conservation of energy, all the energy from the colliding protons must be accounted for in the particles that fly out. But if extra dimensions exist, some of that energy could vanish. Imagine 2 cars crashing in a closed garage. You measure the sound, the heat, the flying debris. If your accounting shows a significant amount of energy is simply gone, it suggests something escaped the garage, perhaps through an open window you did not know was there. At the LHC, that open window could be the bulk. If gravity is free to leak into higher dimensions, then collisions could produce gravitons, the hypothetical particles of gravity, that immediately depart our brain, carrying their energy with them into the hidden bulk. Detectors like ATLAS and CMS would see a dramatic imbalance, a collision where a large amount of energy seems to have disappeared into thin air. Another, even more dramatic possibility is the creation of microscopic black holes. If gravity becomes strong at small scales due to extra dimensions, the immense energy density of a proton collision could, for a split second, warp spacetime so severely it pinches off into a tiny black hole. This would not be a cosmic monster that swallows the Earth. According to Hawking radiation, it would evaporate in an instant, exploding into a distinctive shower of high-energy particles. Finding such an event would be a direct, undeniable signal that the fabric of space can tear in ways only possible if our universe has more than 3 spatial dimensions. While the LHC probes the high-energy frontier, another hunt is underway at the opposite end of the scale. In quiet laboratories around the world, scientists are conducting exquisitely sensitive tabletop experiments to measure gravity itself at distances smaller than a millimeter. Newton's law of gravitation has been tested for centuries over planetary distances, but its behavior at the microscopic scale remains a mystery. If extra dimensions are curled up at a size we have not yet probed, gravity should begin to deviate from its familiar inverse square law at those tiny scales. These experiments use ingenious devices like torsion balances, where a tiny paddle is suspended on a thin wire near another mass. Any extra gravitational attraction from the hidden dimensions would cause an almost imperceptible twist. Others use oscillating cantilevers like microscopic diving boards to sense minuscule forces. They are essentially trying to feel the texture of empty space, to detect if the gravitational field lines are beginning to slip into unseen directions at separations thinner than a human hair. These are not thought experiments or philosophical musings. They are active, rigorous investigations happening right now. The data from the LHC's collisions and the subtle twists in a tabletop apparatus are the raw materials from which a new picture of reality is being built. Every time a proton beam circulates or a microscopic cantilever vibrates, we are sending a probe into the dark, asking the universe a direct question about its true shape. The detectors stand silent, waiting for an answer written in missing energy or a deviation in force, a signal that our dimensions are not alone. 30 theories have taken us from vibrating strings to branching timelines, from holographic screens to simulated realities. Stepping back from this dizzying array, a single, profound question remains. If even one of these ideas is true, what does it say about the nature of existence itself? Does a universe with hidden dimensions feel more mysterious, or does it reveal a deeper, more elegant order beneath the apparent chaos? For centuries, we saw the cosmos as a single, magnificent stage, with humanity as its lone audience. The discovery of other galaxies was the first great humbling. Now the possibility of a multiverse, in any of its forms, represents a second, far more profound revolution. It shifts our story from a unique creation to a single possibility among countless others. This can feel unsettling, even diminishing. The idea that our universe, with all its beauty and tragedy, might be one of many can challenge our deepest notions of uniqueness and purpose. Yet there is another way to see it. This vastness is not a dismissal of our significance, but an expansion of the canvas upon which existence is painted. The laws that allow for life, for consciousness, for the emergence of stars and planets are not arbitrary. They are the specific, rare conditions that allow a universe to become self-aware. In a sea of silent or chaotic possibilities, our cosmos sings a complex song. We are not accidental tourists in a meaningless void. We are the universe's way of knowing itself. The search for hidden dimensions, then, is not just a technical pursuit. It is the latest chapter in humanity's oldest story, the quest to understand our home. Whether the answer lies in curled-up geometry, colliding branes, or branching quantum paths, each theory is a testament to our relentless curiosity. It means our reality, for all its solidity, is permeable, connected, and far grander than our senses can ever reveal. Look up at the night sky. Every point of light is a sun, likely with its own worlds. And now consider that every point in that vast darkness, every star and every space between them, may harbor folds of reality smaller than an atom, or gateways to realms forever beyond our reach. This is not a cold, mechanical universe. It is a living, breathing architecture of unimaginable scale and depth, and our ability to question it, to probe its secrets, is perhaps the most wondrous dimension of all. From vibrating strings to cosmic holograms, this exploration has charted a universe stranger than fiction. We have journeyed across 30 mind-bending ideas, each proposing that our familiar three-dimensional reality is merely a fragment of a far grander, hidden whole. The solid world around you might be a holographic projection from a distant, two-dimensional boundary. The force of gravity could feel weak only because it leaks into dimensions we cannot see. Our entire cosmos may be one of infinite bubbles in an eternally inflating sea, or a single page in an endless book of mathematical realities. The very flow of time and the spark of consciousness might themselves be shadows cast by a higher dimensional geometry. This is not about replacing our world with fantasy, but about uncovering a deeper, more elegant architecture beneath it. the quest for hidden dimensions transforms our universe from a lonely stage into a vibrant, interconnected nexus of possibilities. It suggests that every mystery, from the quantum to the cosmic, might find its resolution not in what we see, but in what lies just beyond our perception. So we leave you with this final, open-ended question. Which of these hidden dimensions resonates most deeply with you? Does the idea of a holographic universe, a brain-world collision, or a simulated reality feel most compelling? And what do you believe that choice reveals about the true nature of existence? Share your thoughts in the comments below and let us continue this conversation. If you enjoyed this journey to the edge of understanding, be sure to like this video and subscribe for more explorations into the profound mysteries of our cosmos.